All right, so we left off yesterday talking about volumetric efficiency, or lack thereof of volumetric efficiency. We talked about the basic four strokes, which were, what are the four strokes? Intake, compression, power, exhaust. What are the five events?
Intake, compression, ignition, power, exhaust.
Okay, and so we were going to talk about, well, in our simplistic model, the valves either opened or closed at top dead center or bottom dead center. I said, well, that's not really that accurate. So now we're going to talk about what is accurate. And this is that drawing out of your book, which even when I know what they're talking about, I look at it and go, I don't know what you're talking about. So we're going to make that a little more simplistic and make a little more sense of it. So let me see, we should clear this off. There we go, fresh piece of paper. And we're going to talk about the intake valve first.
Number
6, intake valve. Intake valve. And this valve timing is from the FA book. So this is from, I think I wrote this yesterday.
Yes.
From FA book. Number 1, the point that I wrote here is the intake valve opens. Now this is just their example. 50 degrees before the piston reaches, you did what in your cup? Reaches top dead center. And this allows well, let's back before I finish that. So let's talk about what we got going on here. I'm going to go to this piece of paper right here. And if I do this right, let's see. Normally I do it on the board, so we'll see how it goes. This 1, 2, 3, 4. Perfect. All right. So we'll call this intake. Intake compression. Power. And exhaust. These are my strokes. And I can use this is my piston. Intake. Piston goes from the bottom to the top, top to the bottom. Top to bottom. Okay then. So top to bottom. And that's my piston travel right there. It goes top to the bottom. So this right down here is bottom dead center, and this would represent top dead center. So then from compression, it goes from the bottom to the top. You see what I'm doing here? Yeah. All right, down and then up. All right, so that's my piston travel. And we will let blue, because that's the color of avgas, blue is my intake valve. Ooh, I messed up. I should have used red. Red is my exhaust. Now what color am I going to use for exhaust? I guess I have to use green exhaust. Very wrong color for that. And according to this drawing, I just said that the intake valve opens 50 degrees before the piston reaches top dead center. So it opens 50 degrees, so it's opening over here. We'll just put a little 50 degrees. That's when it opens. So rather than just being open, I didn't need that line down the middle. Don't know what I was thinking there, but there it is. So we have 50 degrees right there. So far, we know that the intake valve opens. Well, why is it opening up so early? And what stroke it is actually opening up into? This is the exhaust stroke. And so if I were to duplicate it out, I would say right there, 50 degrees, because this is going to be the intake again. This is the intake, right? So we're just looking at the middle. We've got to look at the other ends too. So my intake valve is open way up into the exhaust. Well, why?
At 30 or
50. 50. From the notes. See, notes right here. Opens 50 degrees before the piston reaches top dead center. Remember, this isn't all engines. It's just the example that we're taking out of your book. So what's going on right there? remember, we're talking about volumetric efficiency, and what we have is inside of the cylinder, the piston is coming up, and we have the exhaust valve open, which I haven't really talked about, but is pushing up, and those exhaust valve gases that have been burnt are now traveling from the piston out the exhaust valve and going out. And so what that creates is, I don't know if I can show you something like this. Probably not. No, I can't. So we'll do another little picture. Let me see if I can scroll down a little bit. I can't do that. I need more room. All right. We all know that I'm a terrible drawer, so I will just prove that. So here we have a valve. There we go. And we got another valve. And of course, we'll draw it like that. So we'll do intake over here, exhaust over here, because this has to go out to the exhaust. Intake's coming around like that. Intake, all right, not to scale. So we have all of this nasty, used up exhaust gases are traveling out because the piston's pushing them out. But this creates, if you will, the draft across here, and kind of, I hate to use the word, but I will, sort of a Venturi effect, and that this drawing out creates a low pressure in this area. And because that's a low pressure in this area, it helps to draw the fuel air mixture starts coming in already, even though the piston is actually going up. Right, so there we go, and that's our whole thing. We can start the fresh fuel air mixture kind of start rolling in at us right there, and that's what we want. So this allows the use, there we go, of the low pressure, created by escaping exhaust gases. To pull in and I might as well just FA is fuel air mixture, because I'm going to write that a lot. So, well, if that's good, why not add a little bit more? Why 50 degrees? Why didn't we go 100 degrees before or 120 degrees before? Open it way up. Thoughts?
Too soon? Too hot?
Yeah, what happens if it's too soon? Okay.
Catastrophic.
Well, even my drawing sucks right here. What kind of pressure is in the intake manifold? So this scribble right here is my intake manifold. As compared to, in an operating engine, the air around us. So if the air around us, what is a standard atmospheric day according to the FAA? 29.92, what? Inches of mercury. What temperature? 59 degrees. How many Celsius? 15. Yeah, as a pilot, you kind of have to know that one. As a mechanic, not so much, because the lapse rate makes it easier. But anyway, okay. So we've got this 29.92 around us. What is the pressure inside of the intake manifold in a normally aspirated engine? Vacuum, meaning it's lower than atmospheric. If the throttle valve is closed, what does the pressure do? Go up or down? It goes way down. Significant vacuum. Right? So, you guys are all too young for this. But back in the day, a lot of things were operated off of the manifold vacuum. God, some of these old car guys are fun to have in here. What were some of the cars that actually ran windshield wipers off of that?
Oh, that I don't know, but Datsun 2AZX, the cruise control was operated off vacuum.
Okay. Doesn't help me. Good to know. But like some cars, the wipers would work off of the manifold. The manifold, because there's a low pressure, and so they would run that to a vacuum motor. And so, ironically though, as you slowed down, you would get more vacuum, and the windshield wipers could go faster. And then as you sped up, and there was less vacuum because it was the air equalized. It would start going slower. So not the best idea going on there. But yeah, there's several things that run off the vacuum. So I think some other stuff, but I want to say it was a Volt. That sounds very Volkswagen-ish. Yeah, it sounds very German because Mercedes used vacuum to operate the door locks and stuff too, but I think they used a pump for that. But anyway, try and stay focused here because I'm already losing where I was going with this. All right, so why not open it up way earlier? Okay, because the pressure inside of the manifold is less than atmospheric, and ideally the pressure in our cylinder is more than atmospheric. So if we were to open this valve up too early, those expanding gases that are expanding and pushing the piston down, and the piston is actually, or at this point it's coming back up, it's pushing them out. Well, if the pressure is still too great in there, then you open up the intake valve and it's going to go, hey, let's just go this way. Because it's a vacuum, so it's going to go that way. Well, when you get hot gases that are to a point where it is hot, so exhaust gases are about, roughly 1,400 degrees. There's a range there, but we'll just say at 1,400. 1,400 degrees next to fresh, unburned fuel, properly mixed with air, ready to go, you're going to get?
Explosion.
Yeah, it's going to light that off. And so you're going to get what's called a backfire. Backfire means it went backwards. So you can't open it up too soon because you can get a backfire. All right, so if, what was I going to say? If it's too early, yeah, if valve opens too early. Opens too early. Exhaust gases flow into intake manifold, flow into intake. And ignite the incoming fuel-air mixture. Well, that's not very desirable. All right, so that's what we got there. So we know it's going to open early, but not too early. And we know why it's going to open early, right? The escaping exhaust gases help to start draw in some of that fuel-air mixture. What about closing? So 2. So it closes, this is the intake, about 30 degrees after top dead center. Oops, bottom dead center. So after bottom dead center. There we go. And if we go this one up, so 30 degrees after, not to scale, 30 degrees, and it goes all the way through the intake and keeps going. So this is accurate here. So now wait a minute. We had the piston, make the arrows here. It's going this way. It's going down. Now this way it's going up, down, up, down, up. Piston's going up, but yet the intake valve is still open. So wouldn't you think that the piston comes down, draws in the fuel-air mixture, turns around, starts going up? Wouldn't it start pushing it back out? But it doesn't, because the fuel-air mixture coming in that intake manifold is going to... I gotta be careful what I say. Like some old grandpa, right? It's just kind of moving its way in, right? And it's on its way in. And it's so slow to get in there that it hasn't filled up yet. So it's just like the syringe I was talking about. You know, if I actually had a syringe, it'd be helpful if I brought one in because I have a bunch of them. And like maybe a thing of water, but it had like a small tip and I pulled it really quick, you would see it start to fill up the syringe, right? But I'm still pulling back on it. And I could even start pushing forward a little bit maybe, and it would still have some vacuum in there and would still actually come in. So that's what's happening. So even though the piston has sucked as much as it can, it's turning around. What's above it is still lower pressure than the intake manifold, so let's leave it open until the two equalize. So we could say that's how long it takes for it to equalize before it would make sense there. So leave it open a little bit longer, a little bit more fuel-air mixture into the bucket. All right. This allows the inertia of moving gases, or moving intake gases to fill the cylinder. Before the piston starts compressing. All right, let's talk about the exhaust valve. What is it doing? Well, the exhaust valve opens. Let me see, exhaust valve. Say 1. Scroll up a little bit here. 1. Opens about 30 degrees before bottom dead center. Okay, 30 degrees before bottom dead center. So 30 degrees before bottom dead center. And what am I using? I'm using green. 30 degrees. So we know that the exhaust valve should be open all of the, oops, wait a minute, exhaust valve. What's in my exhaust valve?
Exhaust valve is green.
Oh, I screwed up here. I got my colors all wrong here. Sorry. That's what happens when I get technology here. So this is the intake. And then, oh, this is terrible. I don't know if I can deal with this being so backwards. I just have to do it. This is going to be exhaust valve because it's red. If I don't, I'll screw myself up. All right. So sorry about that. So this is the exhaust valve. We know that it's open through the entire exhaust period, right? Just like we knew the intake valve was open the entire intake period, we know the exhaust valve is open the entire exhaust period, but we also said it opens about 30 degrees before bottom dead center. Well, bottom dead center is there, so we got about 30 degrees before. So we'll bring that out here, and we'll say that's 30 degrees. So it's opening up in the power stroke. Well, what the heck? Why? You know, don't we want to get all the power we can? The piston is coming down. The burning, expanding gases is pushing the piston down. And we're going to wait till we get about 30 degrees before and say, you know what, just pop open the valve. Let's just let it go. Well, the reason why, and this is probably the most critical, I think, point right here in the whole valve timing issue, is going to be that exhaust valve. And the problem is we're talking about exhaust gases that, like I said, are, you know, in the neighborhood of 1400 degrees. It is really hotter than the exhaust valve can take, and to a large degree it's hotter than the oil can take, and there's oil around the exhaust valve stem, and that it cokes up, and we have all kinds of problems with this. So, you know, you talk to an aircraft owner, right? Who's my aircraft owners? Is this just you now?
Gary's gone, isn't
I know. It's just me and you here.
Okay, sir.
You got to back me up. All right. Well, of course, you already know the subject matter, but, you know, what is the biggest fear of every aircraft owner?
Stuck valves.
Stuck valves or burned valves. Either which way, it's our exhaust valves. Everything we think about, oh, my exhaust valve, my poor exhaust valve. You know, the whole rest of the airplane fall apart as you're flying, but, you know, we worry about our exhaust valves. So we got to get these exhaust valves to cool. And the way an exhaust valve cools is by being closed. So the longer it's closed, the cooler it's going to be. So you have to kind of weigh this in there. But here we are opening at 30 degrees too early. Well, that sounds counterproductive. But what happens is by about 30 degrees here left in the stroke, this exhaust gas is doing nothing. It's expanded or used up all of its heat energy that it's going to for work. And now all of the heat energy is going into the cylinder. So you've extracted all the work you're going to, and now you've just got, we'll call it 1400 degrees trapped in the jar, and we're just going to hang on to it in there. Why? So what's that going to do if we just trap it in there and hold it? It's not doing work.
Dissipating heat.
Yeah, it's slowly dissipating.
It's just it's making this hot. How hot is it going to get if we just kept it in there? 1400 degrees. Well, this is going to melt down at that because red line for this is around 400 degrees. So we don't want that. So if it's done doing work, get it the heck out. Right? And that's the whole idea. It's as soon as we figure out it's done doing its work, open the valve, get it out. So that's why it's early. So, yeah, okay. So I'll write some stuff about that. That was a good explanation. There we go. So A.
Can you back up a little bit, please?
Why you gotta be a problem? Why couldn't you write that while I was talking?
Could you go back to the picture? I was trying to see through the picture, but I couldn't see it.
This allows expanding gases to start evacuating the cylinder at the end of the power stroke. The end of the power stroke, and let's see, most of the energy of the fuel air mixture, that's the stuff that was burned, of the fuel air mixture is expended by about 80 to 120 degrees after top dead center of the power stroke. And since a stroke is 180 degrees, it would make sense in this, what they're stating here. So if you're done by 80, you still have another 100 left, or 120, and you still have 50 left. Open up the valve when it's all done. So allowing heat to escape early, or escape as it's written, early. What movie is that from? You know the movie. Nemo, yeah. Early allows engine to run cooler, rather than transferring heat to the cylinder. Heat to cylinder, walls, piston, and valves. Of course, now I did say that what cools the exhaust valve is being on its seat. Here we have a cutaway, and you can see the valve sitting there, and its little seat's right there. And that seat, of course, touches the valve, and then the seat is connected to the cylinder head. The cylinder head is connected to the cooling fins, and that's where it cools. This is the intake, by the way. It doesn't matter, but same thing on the other side. Just for so you know, you can always tell the intake versus the exhaust side of any cylinder. Exhaust side has more fins because it's hotter on that side. This has no fins right here because it's cold air coming. All right, so the thing is, though, you can't cool a valve sitting on its seat if the seat is overheated. You got to have a cool seat. In order to have a cool seat, you got to get rid of the escaping gases. You got to let the gases go that are just heating up the cylinder. So that's why you want the cylinder head temp to be low. It closes about 25 degrees after top dead center to allow inertia, we're coming full circle here, to scavenge remaining exhaust gases. And help bring in the fuel air mixture. So I say closes about 25 degrees after top dead center to allow the inertia to scavenge remaining gases, which is to say that the gases that are flowing just because the piston is now going to start, let's draw it this way. Okay, exhaust valve. It's going to close about, what did it say, 25 degrees? 25 degrees after top dead center. So it's going to close late over here and into the intake stroke. Well, even though the piston is now starting to, see, it's working its way up. Over here, it's going to start working its way down. Even though the piston is now working its way down, it's starting to draw in stuff, which you would think it would then cause the exhaust gases to go up the tailpipe, in and down in the cylinder. It's not, because you have inertia, which means these gases are actually flowing. They've got kind of a mass to them, so they're going, and they don't want to just stop suddenly. So they're just going to keep carrying out, and it kind of draws behind it the rest of the bad gases and bring in the new fuel-air mixture. Ta-da! That's how that works, and that's why it looks like that. Oops, let's go back to this. Let me see. Let's do this here. So exhaust, we've got the exhaust here. And it brings it in right about here to 25 degrees, because that matches that matches that, and that went off in that direction. And there, that's what that looks like. So we've got a couple things to note here. Right here to right here, you see that? Valve's closed. But right here and right here, we have valve overlap. And you are supposed to be able to figure out things like this. There are a lot of FAA questions, and I think I have some too, that give you an engine and it will verbally describe, just as I did right here. If the intake valve closes here, the exhaust valve closes here, what is the duration? How long are the duration is how long valves are on the seat, right? What is the duration? How many degrees of overlap? And so we're going to work through this. I'll clean this up a little bit. We'll do another one and make sure that you can easily do this, because really this is simple. It's simple unless you'd make that drawing. Then I don't know what the hell to tell you. But to me, even though it's messy, it should be pretty simple. So, all right, let's talk about valve overlap. We'll finish some of this off here. So, valve overlap. Valve overlap. So here, notice that I'm being wordy. Notice the intake valve is open 50 degrees before top dead center on the exhaust stroke, and exhaust is open about 25 degrees. So notice, we'll abbreviate intake, opens 50.
Scavenge, the word scavenge?
Yeah. Intake opens 50 degrees before top dead center on exhaust stroke. And exhaust is open 25 degrees after top dead center. Both valves are open at the same time. Same time. This is called valve overlap. Overlap is measured in crank degrees, crankshaft degrees. So what is my valve overlap? Go back to the drawing. How much?
75 degrees.
75 degrees. Well, how do you get that?
50 at 25.
50 before, 25 after. 50 plus 25 is?
75.
75. All right, that wasn't too hard. So this overlap is 75 degrees. Oh, you guys are slow. Go outside and smoke a cigarette. Come on. Does anybody have a cigarette? And matches? And the ability to tell me how to smoke?
I got a lighter and a lung for you.
I smoked a cigarette once when I was in the Navy. And the taste just left my mouth last week. Thank God for COVID, it'd still be there. Uh-oh, Larry's heading my office. You stealing my bubbly? My buble. All right, everybody's caught up? All right, let's try an example here. We're going to do this. Determining valve duration. If the following, so and I believe this is off of a Continental, that's an engine manufacturer, E185. What the heck's an E185? Continental Motors used to label their engines differently than they do now. They changed the designation. So they had the A65. What does the A mean? Well, this is the first letter of the alphabet, that's all. Like you have an O290, and the O means it's opposing. It means it's opposing. So the A65, what did the A stand for? Well, it was just A. It's like before B. And then I don't know what happened to the B and the C and the D, but then they had the E185, and it was just the E series motor, and like the A65 was 65 horse, as opposed to an O290, which is an opposing 290 cubic inch. They did it by horsepower. So E was the E series motor at 185 horsepower. That one is actually 470 cubic inch. So which later became the O470s. But there was a design change in them. So anyway, that was a gee whiz, I guess, as people would say. All right, so the intake opens 15 degrees before top dead center. The exhaust opens 55 degrees before bottom dead center. Intake closes 60 degrees after bottom dead center, and exhaust closes 15 degrees after top dead center. So again, anytime you're given any problem like this, chart it out just like I just did. So we're going to make our grid. So we should have 6. So 1, 2, 3, 4, 5, 6 really. So start one in, intake, compression, power, exhaust. And then what comes next? Intake. What's first over here? Your last? Exhaust. All right, so we got all those. And you don't have to do the piston up, down if you don't want to, but I kind of like to. So intake starts at the top, works its way down, up, down, up, down, down. So I got the piston, which way it's going. And then I remember this is top dead center, TDC, and of course this is bottom dead center. And then I'm going to label in my valves using the right color this time. And so I know that the intake is always going to be open during the intake, for sure, right? Right? There's no doubt about that. We know that. And I know that my exhaust is going to be open during my exhaust stroke, right? In all my examples, it was the whole time, right? Never closed too early. It was always open during the whole stroke, wasn't it?
Overlap is 30.
So now we can move in the overlap. So the intake opens 15 degrees before, so it's over here, it's 15 degrees, right there, 1, 5. So we're going to do the same thing over here, 1, 5. All right, and then the intake closes 60 degrees later. Over here, that's 60. Right, I don't care about over there because I ran out of room. And then the exhaust closes, so we'll do exhaust opens 55. Exhaust opens 55 degrees early. So we're going to bring this over here to 55. And exhaust closes 15 degrees. So we'll go this way. 1, 5. So we'll do it bigger. That's 1, 5 to right there. And then my blue over here is 1, 5. Yep. And then we'll do this. Intake. Oops, this is over here. 1, 5. And over here. 1, 5. All right. Here's my questions. Let's do this. How many degrees of crankshaft rotation is the entire intake valve? Intake stroke. From right here to right here. How many degrees is that of crankshaft travel? Well, how many degrees of crankshaft rotation does it take?
720.
720 to do how many strokes? 4. So there's 4 strokes, 720 degrees. So how many degrees for each stroke? 180. So that's 180 degrees. How many degrees right here? 180. How many degrees right here? 180. How many right here? 180. We can stop there. Okay. So question. Intake is open. How many degrees? How many degrees in total?
255.
I got 255. How do we get 255?
180 plus 60, which is 240 plus 15.
All right, look at what he's got there. He's got 15 right there. Plus 180 plus 60 equals 255. 255. Okay, exhaust is open. How many degrees in total?
250.
So this is one of those defining times right now where, I used to warn you guys, and I haven't in a while, when I'm doing something like this, you'll know, and I always tell you, and I'm always fair, and I'll say, look, I'm going to tell you about something, and don't let this freak you out. If you don't get it, it's okay. See, new people need to know this, right? I always do that. So I'm just going to tell you something. If you get this, that's fantastic. It's deeper. But when I'm taking the time to do something like this, if you are sitting back going, yeah, I don't get that. I hope that's not on the test. It's on the test, or I wouldn't be doing this. So if you don't get it, make sure that you raise your hand and go, yeah, I don't get that. And I'll just say the same thing, but slower. Because that's all I know how to do.
Pretty much what you're doing, right, is you're just taking the blue line on the intake, the 15 and 16, and
Yep.
adding it to the 180 degree stroke for it.
So right here, yep, the 15 plus the 180 plus the 60, add them up.
Oh, that's just it.
That's it. That's how many degrees of crankshaft travel is the valve open?
Okay.
Yeah, you got it. It's like, really? He's like, is it really that simple? Yeah.
Well, I thought it was more complex.
No.
I was confused for a second. I was like, I feel like I'm missing something here.
No, it's really that simple.
All right.
And the reason why, okay, it's not that simple if you do it like this. I can't do it. I literally spent like an hour going, even before class started, I'm like, I know the answer to everything. How do I make the answer fit this? And I still look at it and go, yeah, I don't get what the hell they're doing. And then I do it this way and I go, well, that's just so simple. How could you not understand it? So, all right. So exhaust. How many degrees is the exhaust valve open?
250.
He's got 250 because
55 is 5 less than 60.
55 plus.
Easy math. But yeah, 55 plus 180 plus 15.
Plus 15, so it's the
250.
there equals 250. All right. Smart guy.
It's all right.
No, that was good, actually. Valve overlap
30 degrees.
is how much?
30 degrees.
30 degrees is correct. Why? Because it's right here and right there. So it's 15 plus another 15. So it's 15 plus 15 equals 30. All right. How many degrees are both valves wow, look, I can't read that. Valves closed. So for how many degrees are both valves closed? How much? 245?
255.
255?
180 minus. Oh, shit, no, wait a minute. I messed up on mine. 245.
Okay, remember,
295?
245.
okay, we can only count the 4 strokes. How many strokes do I have up here on my paper?
4.
So I have 6. So we can only look at, oops, we can only look at the 4 strokes. So that is between here and here. I can't count outside of that. So how many degrees on the intake stroke are my valves closed? Are both how many degrees in here are both valves closed in the intake?
0.
0. How many degrees are both valves closed here?
120.
Well, it's 180 minus the 60, so 120. How many here?
125.
It's 180 minus the 55, which is 125. How many are both valves closed here? 0, so it's 120 plus 125 equals 145. See how simple that is? 245. It's so simple I can't even do it. 245. Just got excited, that's all.
I was gonna say, if you draw it out that way, you look at which 2 sections and compression and power, and then subtract
Yeah.
which ones are open.
Yeah, there's different ways. I just wanted to do it how I could write it easily. But yeah, or you can just take another color and just go, well, it's right here. That's the only period right here to here where they're both closed. And how many degrees is that? And that's all that's left. So, all right. You guys did good. You understand that one?
Yeah.
It's smarter than my other class, I'll tell you what.
What's that, Eric?
I thought it was because
What's
of
that,
the
Eric, that had complicated?
Those dummies. No. All right, let's talk about ignition timing.
I need those.
All right. In the same way that valves open early and close late, the spark is early. So, how should I write it? Just like I said it? Seems lengthy. In the simplistic version of the little GIF we saw, ignition always occurred when?
Top dead center.
Boom, top dead center. And that makes sense because here we've got a piston on its way up, and you think about it, if it's on its way up and then you have the spark and the explosion, well, you got to go back this way, right? It's going to kick and go backwards. And that doesn't make sense. Well, why would you have this explosion and then it's going to keep coming up and then compress the explosion and go the other way? Well, 2 things are true about that, or at least one thing. Number one, the example I just gave you, if you try and start an engine and you don't have the spark at top dead center or somewhere behind it, yeah, when the piston's coming up on that starter and you ignite it, it does turn around and go the other way, except it doesn't just do that gently. It explodes the starter bendix, the starter ring gear, and it destroys your engine. And the 470s are all the big Continentals. When I say big bore Continental, so back up a little bit. You understand that there are two manufacturers of engines, and that's all that's left in piston engines. There's Lycoming and Continental. Lycoming is gray, Continental is gold. So Lycoming does their starters external, and they put a ring gear around the front by the propeller, which is teeth around it, and a starter Bendix. It's very similar to what a car would do. Looks more car-ish. Continental has their own very weird way of doing things. And when I was very, very young and freshly married and was very, very poor, we had a washing machine went out. And being an aircraft mechanic, I'm sure I could fix it. I kid you not, the item that made the bucket agitate was the exact same design as the starter on. So I'm like, I get that. When the starter starts on a Continental, it winds a worm gear that winds, so the worm gear winds a drum. That drum is attached to a spring. That spring then tightens up on another drum that then goes in and starts the engine. And when the engine starts, it spins faster than the cog in the wheel, and so it allows it to spin and slip, and then you stop the starter. And what happens when the engine kicks back and it's locked together, it explodes that spring into the engine. It's not external, it's in the engine. So then there's a hole right there, and it just goes right into the sump, and so it destroys the engine. So there you go. And kind of the reason why Continental does it that way in the big engines is because these big old 6 cylinders, right? You can't add another that much to the engine compartment. So the engine is right up against the firewall to begin with, and there's no room to add a starter. They want to add the starter, so the engine's this way, they want to add the starter this way. So it makes it a 90-degree angle drive is how it works. As where with Lycoming, they just put it on the bottom of the engine and go forward. And so that kind of works. Anyway, yeah, so you don't want this. It's important that the ignition timing be at top dead center or later for starting. But you can't do that while you're running the engine, so you have to change it. So let me see. The spark. Okay. In the same way that valves open and close early. Early or late, actually. I kind of blew that one. The spark is early. So timing, call it ignition timing. Is usually about, we'll just say 25 degrees. 25 degrees before top dead center. On which stroke? Yep. Of compression. Well, this 25 varies quite a bit. You know, it can go down to 20, 24. I don't think I've ever seen it past 25. So I got the firing order. Am I really not going to explain why? I'll explain why now. I don't have anything in my notes. Okay, so why is that? Why early? Well, as I mentioned before, the fuel-air mixture does not explode. It burns, and it burns out in a flame front. And all aircraft engines have 2 spark plugs. You guys noticed that on your engine, right? 2 spark plugs. Well, that's normal. That's the way they all are. Why do we do 2 spark plugs? What?
He didn't notice that they had 2 earlier, so I was like, did you notice that?
Okay. Because why?
Two negatives.
Well, why do we have two magnetos? Well, because there's two spark plugs, of course. No. One fires the other one. You got to have two. For safety, it's redundancy in case one fails and the other one keeps you going. Well, these guys aren't stupid when they did figure this out. They're like, well, since we've got two, let's make use of it. And if you shut off one of those ignition systems, you're going to see a noticeable drop in RPM because it's been designed with the two spark plugs the way they both ignite a flame front, and the flame front then moves together and in splits. Instead of starting over here and then going across the cylinder and down, you have it starting in two spots and burning together. Some aircraft engines have staggered timing. One is at 28 and one is at 30. So I guess there is more than 25. I just remember that. And that would be some of these smaller engines. Why? Because they figured out that next to this spark plug, it's leaner and this spark plug is richer. Maybe it's the other way, but one is leaner and one is richer. And lean and rich has to do with the speed of burning, which we'll talk about in the next class. So we do this at 25 degrees before top dead center because we start the flame burning and it's slow enough that it hasn't really started to have this peak pressure wave until the piston is really near the top. And that's when you get this peak pressure, and then it starts to push the piston back down, which then makes more sense. It's break time.